Hello everyone, welcome to Power Electronics lecture number 4. Today's date is 3rd July 2023 and today's topic which we are going to discuss is numerical on half wave control rectifier using resistive load. Last time we have analyzed the circuit and observed the waveforms for a half wave control rectifier. So let's begin with numerical number 1. So numerical number 1 statement is, for the circuit shown below, if the firing angle is 60°, determine the following. What do you mean by firing angle? Firing angle is alpha, right? So alpha is 60°. It is also called as firing angle or delay angle or triggering angle. All are one and the same. So for the firing angle of 60°, determine the following. The average voltage across the resistor. The average voltage across the resistor meaning we have to find out V out average, or V out average is also called as VDC. So we have to find out V out average or VDC. Then the power absorbed by the resistor. So power absorbed by the resistor R will be P out or PDC. And finally we have to find the power factor. So let's analyze the circuitry. So we have an SCR which is applied a trigger pulse over here IG, and your V in RMS value is given as 120 volt, because whatever the value over here written, it's in RMS form. So this value is V in RMS. So that is 120 volt. Then the resistor is 100 ohm. Alpha value is around 60°, and R is around 100 ohm. So let's start solving the numerical. So this is the given data. V in RMS is 120 volt, alpha is 60°, R is 100 ohm, and it's a half wave control rectifier with resistive load. So if I want to find the peak value, it will be RMS times root 2. So it will be 120 root 2. So let's first find the value of V out average. So V out average is given by Vm by 2 pi into 1 plus cos alpha. Now Vm value is 120 root 2 divided by 2 pi into 1 plus cos of 60. All right. And cos 60, you can check it out in your calculators. It will be around half. The value will be 0.5. So please calculate this number and let me know what is the answer of V out average, or we can also call it as VDC. So let me know the number. Okay. The value is coming very close to, let me just cross check this. So this is 2 and this will be 60. All right. So 60 into root 2 into 1 plus half, that is 1.5, and the whole divided by pi. So it's coming very close to 40.51 volt. Okay. So that's the value of V out average or VDC. All right. So now let us next what we have to find out. We have to find the value of power absorbed by the resistor. So let's find out power absorbed by the resistor. Power absorbed by the resistor formula is given by P out, or it is also called as PDC. It is given by V out RMS square divided by R. All right. So that means we have to find the value of V out RMS square. All right. So let's find out the value of V out RMS square. So the formula is as follows. V out RMS square is Vm square by 4 into 1 minus alpha by pi plus sine 2 alpha divided by 2 pi. Okay, so this is the formula. So let us substitute the values over here. One caution we have to take care is this alpha over here alone has to be entered in radians. So this is alpha is 60 degrees conversion of degrees into radians will be multiplied by pi by 180 degree. So this will be around pi by 3 radians. Alright. Whereas sine 2 alpha, here you have to substitute in terms of degrees. So here alpha will be in degrees and here alpha will be in radians. I hope it is clear. Alright. So let us substitute the values. So that is V out RMS square is equal to Vm square, that will be 120 root 2 the whole square divided by 4 into 1 minus alpha is pi by 3 divided by pi. So this will be around 1 by 3 plus sine of 2 alpha, that will be sine 120 degree divided by 2 pi. Alright. So let's find out the value of sine of 120 degree. Sine of 120 degree is, this number is 0.866. Okay, so that's the value of sine of 120 degree in the calculator. Now substitute these values and you'll definitely get an answer which will be closer to, that is V out RMS square is 70. Yeah, so this is around 579 5791.2. Okay, this is RMS square. This number is RMS square. Now actually we have to find out P out. So P out or PDC will be V out RMS square divided by R. So that will be 5791.2 divided by R, and the value of R is given as 100 ohm. The value of R is around 100 ohm. So what's the value of P out or PDC, average output power absorbed by the resistor? It's 57.91 watt. Alright, so that's the value of P out or PDC. Now next we have to find out the power factor. So the third case is, we have to find the power factor. Now power factor is given by the formula V out RMS divided by V in RMS. Now V out RMS will be, this is V out square, so V out RMS will be around 76.1 volt. Alright, so substitute these values over here. 76.1 volt divided by V in RMS is around 120. So if you divide this number, this you will get 0.634. Okay, power factor without any unit, because volt and volt will cancel out. Okay, that's the answer for the power factor. Now always remember, there is one advantage of calculating power factor. Its value will be always between 0 to 1. Okay, excluding 0 and 1, it always between value 0 and 1. Power factor value will be between 0 and 1. Alright, so we'll do one thing. Let us simulate this in LT Spice and check it out whether the answers are quite close or no. Alright, so let's go to LT Spice. So we have already made the circuit and we have made it, given the value of pulse in such a manner that alpha is coming out to be around 60 degree. So let us simulate. We have simulated and kept the waveforms. Alright, let me change the color to around a little bit dark color. Yeah, this is my V in and that's my V out. Let me plot IR separately. Yeah, this is my V out. Alright, this is my voltage across the SCR. This is my gate current and this is my load current. Okay, load current and output waveform nature is same. As you can see, the unit will be different. Alright, now here what we have done is we have given input in the form of a peak value because the RMS value was around 120. So we have to give over here peak value. So it will be 120 into root 2, which will be 169.7. All right. Frequency is given as 50 Hertz. So this is my circuit with a resistive load. R is around 100 ohm. And these are my waveforms. Now let's check the value of V out average. So I will just keep the screen half. So for finding the value of V out average, just click on control and press on the V out. So V out average is coming out to be 40.3 and we got the answer as 40.51. That's reasonably good and close because here we are using an actual SCR, so there will be a slight voltage drop across the SCR. And here we are not assuming any voltage drop at all. All right. And also we are assuming that output is exactly equal to Vm. It is not in actual case. There will be some voltage drop. All right, we have to find the value of V out RMS. V out RMS is coming out to be 75.75 and we got it close to around 76.1. That is also quite close to each other. So yeah, so via simulation, it's verified that average value of the output and the RMS value of the output is quite close. All right, in this way, you can check your values in LT-Spice. All right, so that's about checking the values in LT-Spice. Now let's go to the next numerical. In numerical number 2, we have a controlled half wave rectifier has an AC source of 240 volt RMS at 60 Hz. The load is 30 ohm resistor. So this is the value of RL. So we have to determine the following. We have to determine the delay angle such that the average load current is 3 ampere. So what is the average load current given by? Average load current is given by I out average. All right. So that is given as 3 amperes. And we have to find the value of alpha. Then we have to find the power absorbed by the load, that is PDC or P out, and then the power factor. All right. So let us see what is the given data. So given data is we have given the input supply. V in RMS is 240, R is around 30 ohm, and I out average is around 3 amperes. So let's draw the diagram just for the mental picture. So here we have AC source. Then we will have an SCR. SCR will have its gate terminal over here. Then it's connected to a resistive load. Here I check the output V out. Here is my resistor RL. We can consider it RL. This is my SCR and this is my V in value in RMS, which is around 240 volt. All right. And what else is given to you? The current flowing. So this value is given to you IDC, which is around 3 amperes, and the value of resistor is 30 ohm. So this is the picture given to you. All right. So let's start solving it. So first of all, let us write what is given to us. I out average is given to us. Its value is 3 amperes. But I out average, another formula will be given by V out average divided by R. All right. So that's the value of I out average. It's V out average divided by R. We can write this only because it's a resistive load. All right. Now, what is the formula for V out average for a half wave control rectifier? It's Vm by 2 pi. This R will come as it is over here into 1 plus cos alpha. All right. And this entire equation we equate it to 3 amperes. Let us see what is available. Vm is available. Alpha we have to find out. And R is available. I mean, we can substitute it as R or RL. Let us take it as R only. All right. Let us continue the numerical. So R value is around 30 ohm given to you. Vm value we can calculate as 240 root 2. So yeah, let us cross multiply and check what we get. So here we have 1 plus cos alpha will be equal to this 3 ampere multiplied by 6 pi into 30. All right. So that will be around 6 pi into 30 and divided by Vm. And Vm value is how much? 240 root 2. I hope it is clear. This 3 multiplied by 2 pi, that is 6 pi. R value is 30, and this divided by Vm. Vm is 240 root 2. So yeah, so cos pi will be given by this quantity, which is 6 pi into 30 divided by 240 root 2 minus 1. All right. So from here we can calculate this. That is, alpha will be equal to, this number is coming out to be cos inverse of 0.665. So if you do cos inverse of 0.665, you will get angle as 48.3 degrees. So this is the value of alpha, which is the firing angle. Now let us find a firing angle in radians also. So radians will be 48.3 degrees into pi by 180 degree. All right. So if you calculate this, you will get it as 0.842 radians. Now this will be very helpful when we calculate RMS value. Okay, so this is the value of delay angle or triggering angle or the firing angle alpha. All right, if the average value of the current is given to you as 3 amperes. All right, this is about your alpha or the firing angle. Now next point, let us calculate the value of PDC or P out. So it is given by V out RMS square divided by R. All right, so that's the value given to you. Now that means you have to calculate V out RMS square. So the formula is given by Vm square by 4 into 1 minus alpha upon pi plus sine 2 alpha divided by 2 pi. So remember, yeah, we have done this before. So here we get as V out RMS square will be equal to, your Vm is around 240. Let us check. Yeah, Vm is around 240 root 2. So 240 root 2 square divided by 4 into 1 minus. Now alpha we have to write in radians, so it will be 0.842 divided by pi. Pi you substitute it as in radians again, it is 3.14. Okay, plus sine of, we have to substitute now alpha in radians. So 48.3 into 2, that will be around 96.6. So sine of 96.6 degrees divided by 2 pi. All right. So sine of 96.9 will be around, this value is around 0.9934. Okay, 0.9934 divided by 2 pi, and pi over here is 3.14. Okay, you can continue. So this will be around 6.28. All right, so if you plug in all the answers, you will get the value of V out average as V out RMS square as, so that is V out RMS square will be equal to 25632. Okay, that's the number which we get, and we need to find the value of V out average from here. So V out RMS here from here, RMS will be around 160.1 volt. Okay, so that's the value of V out RMS which we get. So from here we have to calculate PDC. So PDC will be equal to V out RMS square. Just a second. Yeah, PDC will be, okay. It's a loading a little. So yeah. So now we have to find out P out or PDC. That will be V uh, out RMS square divided by R. So that will be 25632 divided by R, and R is around the values, let us check it out, it's 30. So if you divide this number, you will get the value of PDC as 854.4 watts. So that's the number of average value of output power. Now also we have to find out the power factor. So power factor is given by the formula V out RMS divided by V in RMS. V out RMS is 160.1 volt and V in RMS is around, I think 240 given to you, right? 240 volt. Yeah. So this number is coming out to be 0.667. All right. So this is the value of power factor. It is between 0 and 1. So it seems to be correct. All right. So this is how we can solve a simple numerical on half wave control rectifier. Okay. So this completes the numerical number 2. And if they ask you in the exam, normally this will come for around, let's say, 10 marks. Okay. Yeah. So we have solved two numericals on half wave control rectifier. Now let us move on to the next topic. So next topic is some of the performance parameters of the rectifier. We have seen some of them. That is power factor, then the rectification efficiency, form factor, ripple factor, or we call it as a voltage ripple factor. Then we have a transformer utilization factor and the PIV rating of the SCR. Okay, PIV rating is nothing but peak inverse voltage. So let us check it out one by one. First of all, we have output DC power, or it's called as P out or PDC, which is given by the formula V out average into I out average, or it can also be written as PDC is equal to VDC into IDC. All right. So this is the formula for the DC output power. Now the output AC power is given by the formula V out RMS into I out RMS. Okay, the output AC power is given by V out RMS into I out RMS. Now, the effective RMS value of the AC component of the output voltage is given by VAC. Now let's consider this is my output waveform for a half wave control rectifier. So this entire peak is my AC ripple or the AC component, right? And this is my VDC. Let's say this red color represents the average value of this waveform, and that is around, this is my DC value of the DC component value. All right. So what is VAC? It's a square root of RMS value of the output square minus average value of the output square. All right. So next we'll find out the form factor. Form factor is the measure of the shape of the output voltage. So basically it's a ratio of V out RMS divided by V out average or VDC. So it's very important to know the value of the formula for the form factor, the effective value, RMS value of the AC component of the output. All this will helpful with the solving numerical. Now the ripple factor is the measure of the ripple content in the output. All right. So ripple factor is given by VAC upon VDC, where VAC is given by this formula and VDC we already know the formula. So, but we most of the time, we calculate in terms of form factor. So once we get the form factor, ripple factor will be square root of form factor square minus 1. Now, if we use the transformer, right, it will be a step down transformer, then we have to calculate the transformer utilization factor. So basically it is PDC or P out average divided by VS into IS. Now VS is the RMS value of the secondary voltage. So let's say this is around 1000 volt, and at the secondary we get around 200. Okay, so this two secondary voltage of the transformer in the RMS form is my VS, and IS is the RMS current of the secondary current. Okay, of the transformer secondary. So the current flowing over here is my IS. All right. So this is the transformer utilization factor. Next, we talk about the PIV rating. Now, PIV rating is the maximum reverse voltage that a diode can withstand without any damage. Okay. So let me explain it to you. Let me go to LT-Spice and let me check out the waveform for the voltage across the SCR. Now, this waveform is voltage across the SCR, right? Now, here we have, in the negative half cycle, During the negative half cycle, the voltage across the SCR reaches to minus of minus 169, as you can see. It reaches to minus Vm value. All right. So that means in the reverse bias, the voltage across the SCR is minus 169. In case of input is 120 volt RMS value, this is the peak value. So it's reaching minus Vm. So that means your SCR should be able to hold this much value. So if the SCR is able to withstand this much value without getting damaged, that's the value of PIV rating. All right. So I hope it is clear. So the maximum reverse voltage that can be applied to an SCR without damaging it in the reverse direction. So that is my PIV rating of the SCR. Now, summarizing all the ideal characteristics of rectifier, it should it should have 100% rectification efficiency. Form factor should be 0 or very low. Ripple factor should be 0. The effective RMS AC component should be around 0. Transformer utilization factor should be 100% or 1. And the power factor should be unity. So these are all ideal requirements for a rectifier. All right. So that's it for today's topic. Thank you all for joining.